Oh, okay. Thank you. As Yvonne said, I'm going to, in 20 minutes or less this morning, give you a very quick summary of where we are with the LRO mission and the mission operations, a quick summary of just a few of the highlights of the science results so far, and then I'm going to give you a preview of our extended science mission objectives. Now, there we go. For future speakers, the trick is you have to point over there in the corner, not at the screen. For those of you who are not familiar with LRO, LRO was launched just about 3 years ago. It contains 7 instruments that are listed here. The instruments are designed to give us the next set of maps of the moon, high-resolution imaging of the moon, and other information about the moon that's important not only for science, but for future exploration. The quickest way I can tell you about the LRO instruments is through a 55-second video. This shows the LRO spacecraft drawing, and the other images here are the assembly of the spacecraft. Crater is a multi-MeV energetic particle spectrometer. Diviner is an infrared radiometer to measure temperature and composition of the lunar surface. Lola is a 5-beam laser altimeter that fires 140 laser beams per second. LROC consists of high-resolution narrow-angle cameras and a wide-field camera. LAMP is a far UV spectrometer to measure the surface. LEND is a Russian instrument to give us high-resolution maps of subsurface hydrogen. And Mini-RF is a synthetic aperture radar system that operates at 2 frequencies. This shows the spacecraft at Goddard prior to launch. It's a Discovery-class spacecraft. The LRO spacecraft, these are a summary of the instruments in case the movie didn't work. The LRO spacecraft has 2 important features. One is the enormous amount of data that we get from LRO. We have a dedicated ground station at White Sands, New Mexico, operated by Goddard that gets every single orbit when the moon is visible. And so we download an incredible amount of data. So far, LRO has deposited in the PDS 325 terabytes of data, which is more than half of the holdings of the PDS currently. We put into the PDS roughly 5 terabytes of data per month from LRO. The other important factor is that the LRO spacecraft consists of essentially a fuel tank with the spacecraft wrapped around it. We have an enormous orbit adjust capability that gives us a fair amount of maneuverability. We used about 2/3 of the propellant to get into our low altitude around the moon. And then we've used the rest of the fuel for orbit maintenance. The next chart here shows the graph in the lower right gives the orbit history of LRO. The scale, for those of you who can't read it, is 0 kilometers at the bottom up to 250 kilometers altitude. We were launched in June of 2009 into an elliptical orbit. This is what's called a frozen orbit. It's very stable and easy to maintain. We stayed in that orbit for about 3 months to calibrate and validate the spacecraft and instruments. And then in September of 2009, we dove into our 50-kilometer mapping orbit. And in that orbit, a 50-kilometer altitude, if you don't do any orbit maintenance, you'll impact the surface in less than 3 months. So every month, we would use about 6 kilograms of fuel in order to raise our aposaline, to raise our parasaline, so that we always stayed between 35 and 65 kilometers altitude. That was for the 1-year exploration mapping mission. After 1 year, we were converted into a science mission and moved into the Science Mission Directorate. And then the science team did a very thorough analysis of all the types of orbits we could do for our science mission. We decided to stay in the 50-kilometer mapping orbit as long as we could, which, with two exceptions, in August and November of last year, we lowered our parasaline so that it was over the Apollo sites at an altitude of about 25 kilometers altitude. So we did high-resolution imaging with about 25 centimeter spatial resolution of the Apollo sites and other sites of geological interest in that region. Then last December, we were running out of fuel, and we're down to 60 kilograms. We used 620 kilograms to go back into this frozen orbit where our parasaline is about 30 kilometers anchored over the South Pole, and our aposaline is below 200 kilometers over the North Pole. And this is an excellent orbit for studying southern hemisphere and polar features. So we have a 2-year science mission that ends in September. We submitted to SMD this spring a proposal for an extended science mission for 2 more years of operation, and now we're waiting word from headquarters as to whether we'll continue operations for 2 more years. Now the question is, why do you want to do 2 more years of measurements? Well, first of all, the measurements are very important. As it says at the bottom of the plot here, more measurements enable new science, and they fill strategic knowledge gaps, a phrase you heard earlier today from Mike Wargo, for future exploration planning. Now, the instruments all benefit from additional measurements. At the top, for those instruments that are doing targeting, like the camera, like Diviner, like Lola, that measure narrow fields of view, we get better aerial coverage. We fill in gaps that now exist in some of our measurements. Other measurements like the neutron detector and the UV spectrometer that are integrating instruments, more measurements give you better statistics, better spatial resolution, better accuracy. And then finally, we're going to make several new unique measurements. First of all, we're going to measure energetic particles at solar maximum, which are very important for the moon. And then also we're going to try some new measurements, for example, bistatic radar measurements using Arecibo and Mini-RF. Now the science objectives for the extended science mission, we align those with the priorities of the new planetary decadal. They're organized into the 4 themes you see here. Our whole focus of our proposal was to show that we can give us more LRO measurements, certainly improve our understanding of the moon, but they also improve our insight as to how processes operate in the inner solar system. What I'm going to do for each of these 4 themes now is very quickly tell you some of the highlights, just some of the highlights of what we've done so far, and then give you some examples of new things we're going to do in the extended science mission. I also want to remind you that we've got an enormous number of papers that are coming out. We have a special theme issue of JGR planets that'll have roughly 30 LRO papers, and that's due out in a few months. And at this meeting, there's many presentations by the LRO team. The first theme are volatiles. The first theme are volatiles in the polar regions. With LRO, we try to have as our first objective to characterize the permanently shadowed regions by measuring their temperature. We've discovered with the Diviner that the polar regions are colder than expected, and certainly cold enough to sequester volatiles. And also we measured the topography with high precision in order to measure and predict illumination conditions at the poles. The other objective we had for the science mission was actually to measure the volatiles and to determine where they're located. The hydrogen maps shown here from land have the very intriguing result that some permanently shadowed regions have volatiles, have subsurface hydrogen, like Cabeus and Shoemaker. Others do not have hydrogen in the permanently shadowed regions. And there are some that are some areas outside of the PSRs that are solar illuminated that appear to have hydrogen. We've also been measuring the surface with active techniques like LOLA. This left-hand panel shows a graphic of Shackleton Crater, where in a recent paper in Nature by the LOLA team, they've measured the reflectance of the surface and have determined that there's a high probability of water frost on parts of the surface of Shoemaker. The UV spectrometer has been used in the upper right here to look for frost, looking at the UV reflectance characteristics. They've determined that some craters, like Hayworth, do have water frost, and others, like Shoemaker, that we think have subsurface hydrogen, does not appear to have frost on the surface. So this is a very puzzling and very significant result. Now, what are we going to do in the extended mission? Well, the first two bullets show some new measurements regarding PSRs. First of all, we're going to attempt, as shown in this graphic, measurements where we transmit with Arecibo, and then we measure the reflected signal detected by LRO. And the important thing here is that it's not a specular or direct reflectance. It's reflectance at an angle which can be used to unambiguously separate rocky regolith from icy regolith. The other important measurement is to take the narrow angle camera and see whether we can use earthshine to actually look at the high resolution structure within the PSRs. The other bullets are actually improvements of current measurements that we've been making. Now, the second theme is the early evolution of the moon and geological processes that have continued. The first upper graphic shows some results from the LROC experiment where they've looked for scarps and graben and their global distribution. These are basically wrinkles and cracks in the lunar surface that are consistent with a relatively recent contraction of the lunar surface, showing that the moon is now still contracting and perhaps more active than was originally expected. The bottom panels show measurements of the Compton-Belkovich anomaly that are made with a variety of instruments, and these prove very conclusively that the Compton-Belkovich anomaly is a isolated far side volcano in the highlands, which is an important result. Now, what do we do with these themes, this theme and the extended mission? Well, first of all, we're going to make continued measurements of temperature in the very cold regions of the PSRs, and by studying those temperature variations with time, the Diviner team hopes to be able to put a constraint on heat flow from the interior in these cold polar regions, which will be a real breakthrough as far as understanding the temperature structure and temperature constraints of the moon. We're also going to continue the studies of volcanic features on the moon. The bottom right panel is the Ina D caldera, which is being studied at the present time. Another important measurement in the extended mission is going to look at the chemical composition of central peaks of the larger craters. These central peaks are formed by an uplift of material during the impact. The early Diviner results, which are shown here at the bottom right, show that the central peaks often have chemical composition that's different than the surrounding terrain. And I cannot, if I mention the term central peak, I really feel obligated to show this really wonderful, inspiring, what I call an Ansel Adams portrait of Tycho crater, Central Peak, at sunrise. The beauty of this image, aside from the inspirational value, is to look at in detail with a resolution of meter scale of all of the features, the slopes, the boulder at the top, and to try to understand the processes that produce this as a rebounded uplift of the lunar surface when Tycho crater was formed. Now, the third theme is the lunar impact record. A very early paper from LRO is this one by Jim Head and colleagues that appeared on the cover of Science nearly 2 years ago now. The Lola team did an inventory of all craters greater than 20 kilometers in size and showed that the crater distribution is preferentially larger in the highlands than it is in the mare, and this is a clue that the impactors that formed the oldest, earliest craters on the moon had a different size or energy distribution perhaps than those that formed later on the moon. And this has implication for our understanding of the bombardment history of all the terrestrial planets. In the extended mission, an important, and I should mention that the Jim Head paper in the last one was based on the first few 100 million topographic points measured on the moon by Lola. We're now up to over 8 billion measured points on the lunar surface for topography. And the moon is now the object in the solar system whose shape and topography is best understood, even better than that of the Earth, because the Earth is 2/3 ocean, and we understand the topography of the moon better than we do that of the global Earth. This illustrates an important new measurement that's going to be made in the extended science mission. We expect to make more stereo measurements. The upper panel shows a panchromatic image with LROC in high resolution of an impact melt feature where you can trace out 2 impact melts, and the arrows show what you think to be the flow directions. By adding the high resolution stereo digital terrain map, you can really see how the flow formed and trace it back to its origin. Thank you. Another important continued and new measurement in the regarding solar system bombardment concerns looking for fresh craters. The LROC team has compared Apollo imagery from the 1970s with corresponding images taken with a narrow angle camera. And you see in this case circled in red a fresh impact crater that did not appear in the Apollo images. And these are small impact, small craters. And you can use this over this 30-year time span to get insight into the size distribution of very small impactors in the moon. And now by taking over a longer time span of NAC data, this process can be automated, and we hope to really improve this result. And finally, regarding impact record, we want to continue to look at the large craters and the roughness and boulder distribution. This shows Lola maps of Tycho of just roughness from the 5 beams, and you can see that the rough regions are interior to the crater. Similarly with Diviner, the temperature maps, this shows for Copernicus the fact that the temperature maps show that even though the outside is smoother, there are evidence of subsurface buried blocks in rough material. And then here's a NAC image of the central peak of Copernicus crater. The last theme is interactions with the external environment. This is primarily through energetic particles, and now During the science mission, we made the first searches for the atmosphere of the moon, and this is the discovery set of data of helium, the first measurement of helium in the lunar exosphere, and with the LAMP instrument. And this is a very new result that's just been submitted to Icarus, where the LAMP team has measured the distribution of helium as a function of time as the moon goes into the magnetosphere, and the helium essentially is dramatically reduced. This shows that much of the helium in the atmosphere comes from the solar wind, and so you don't have the solar wind bombardment while the moon is in the magnetosphere. The other important interaction with the external environment are energetic particles. This is the full history of the MEV particles striking the moon. We're launched as solar min, where the cosmic rays were greatly enhanced because of the quiet sun. Then as we move now into solar maximum, we see the cosmic rays declining, but we get these very short-lived energetic particle events. Now these are very important not only for radiation effects on humans, but also to understand subsurface processes. The Crater team has a very provocative paper where they identify that cosmic rays go down about 2 meters, the energetic particles go 1 meter or less, but that they deposit significant energy, so that if you have ices below there, this energy can actually disassociate material. And this may be an explanation as to why in the L-cross event we detected CO and H2, both of which were unexpected, but they may be due to subsurface chemical processes initiated by cosmic rays that disassociate primitive ices. Now let me conclude with the last slide, which I want to just point out that an important objective of LRO has been not only to get out our science results and put our data into the PDS, but it's also to tell the LRO story to the public. We have a very productive outreach and public affairs projects that we not only get the information out, we have visualizations to support it. We are strong supporters of International Observe the Moon Night. And we also try to get our images out, not only to tell people that the moon's a wonderful place, but also to inspire them as to the beauty of the moon and the past exploration of the moon. So hopefully there'll be future exploration. Thank you.